The last problem I want to do is looking at something called the common ion effect. So this is mercury 1 carbonate. So if I have a mercury 1, which would break up into Hg1 plus, and then carbonate is CO3 2 minus. And instead of seeing how much water it dissolves in, we're going to try dissolving it in 0.5 molar sodium carbonate. Okay, so let's take a look at this. This is my equilibrium, Hg2CO3, and I'll put some paper underneath it so you can't see everything. It splits up into these two things here. And instead of being 0, so this is 0 because there's no extra Hg, but carbonate, well, I'm taking 0.5 molar sodium carbonate. Sodium, we know, that is always a spectator. But carbonate is not a spectator. And if I have 0.5 molar sodium carbonate, this is no longer 0, but it's 0.5 molar. Okay, so this is called a common ion. If I add more stuff here, according to Le Chatelier's principle, what will happen to the equilibrium? Well, it should shift this direction because this is my solid. I add some of this, it's going to shift to alleviate the equilibrium, and it's going to make more solid. So less will actually dissolve. So let's figure out how do I solve this problem now. So I have this is plus 2s, this is plus s, this is 2s, and this is now 0.5 plus s. Okay? And so now the question is, what is my molar solubility? S is question mark. And they gave me the KSP in the problem above. So my KSP here for this is 3.6 times 10 to the minus 17. Okay, that equals Hg squared times CO3, like that. Well, let's plug in my stuff here. So my 2s is going to go into here. This is 2s quantity squared. And this is 0.5 plus s, like that. But s, we know, that is a really small number. Compared to 0.5, is s sufficiently small? And in most cases, yes it is, because this is going to be really, really small. This is 0.5, which is pretty big. So we're going to get rid of this. We're going to say this is small. So my math becomes simplified a little bit. So this becomes 4s squared. So I take 2s times 2s times 0.5, like that, which ends up being 2s squared, so 0.5 times 4. And that is 3.6 times 10 to the minus 17. Okay? So now if I solve for s, take both sides, divide by 2. So 3.6 times 10 to the minus 17 divided by 2. 1.8 times 10 to the minus 17 equals s squared. Square root that. S is equal to 4.24 times 10 to the minus 9 moles per liter. Okay, so that's how many moles can dissolve in 1 liter, which should be a lot less than what it would be in water, because if I did this, if I just solve for without this 0.5 here, so if I had 4s and this was s, so 4s cubed, then my s would be a lot smaller, just by doing the math. And it makes sense, because if I take 0.5 molar of this and I add it to my equilibrium, it's going to shift my equilibrium this way. Less of this will dissolve, and I will have more solid here. So that's the common ion effect in solving KSP problems.